Okay, welcome students back to chapter 2. We're going to continue on with section 2.2, matrix algebra. Okay, 2.2, matrix algebra. Okay. If A and B are two m by n matrices, okay, then A plus B is equal to all the elements of I, J, plus all the elements of B, uh, uh, B, I, J. So we just match element to element. They have to be the same dimensions, n by n matrices. Okay, and if they're the same dimensions, then we just add up corresponding entries for all the entries. Okay, or elements. Okay, if I multiply a scalar times a, that's going to be Saij. Okay, so I'm just going to multiply that scalar times every element of the matrix for all entries in A. Okay, where S is a scalar. Okay. A minus B is equal to A plus -1 times B, okay, which is equal to Aij minus Bij for all entries. Okay, so pretty straightforward. Okay. Let's do an example. Okay, I have A, matrix A equal to -2, 1, 0, 4, -1, -3, 2, and 2. I have B equaling 6, 3, -3, 3, -3, 3, -2, -5. Okay, and I want to subtract these two. So A minus B. Okay, so I'm just going to subtract term by term. Basically, I'm going to be adding the opposite of B. Okay, so -B opposite of B. It would be A plus -1B. Okay. I'm going to take these and I'm going to take -2 and I'm going to match up the entry. So I want to do -1B. If I negate B, if I do -1B, -1 times B, that's -1 times everything in here. Okay, and so that just would change the, let me bring this down a little bit. That would change the sign in everything. Okay, so -B or minus B would be -6, -3, +3, 3, -3, +3, -3, +2, and +5. Okay, so if I want to take A plus -1 times b, then I'm going to say that this will combine into -2 plus the opposite of 6, which is -6. That's my first entry. My second entry in the first row, second column, is going to be 1 plus -3. The next one going over is 0 plus +3. And the next one going over is 4 plus -3. Continuing on to the second row, this is -1 plus 3. This is -3 plus -3. This is 2 and 2. And then 2 and 5. And so my resulting matrix is a 2 by 4 matrix. Okay, I started off with two 2 by 4 matrices, A and B, and I end up with a 2 by 4 matrix. Okay, same size. 2 by 4 meaning 2 rows and 4 columns. So -2, -6 is -8. 1 and -3 is -2. 0 and 3 is 3. And make these a little closer together. 3 and 4 and -3 is 1. Okay, -1 and 3 is 2. -3 and 3 is -6. 2 and 2 is 4. And 2 and 5 is 7. Okay, so we successfully subtracted those two matrices. Got a matrix of the same size, same number of rows, same number of columns, same dimensions. Okay. Matrix multiplication works a little differently. Okay, we multiply row entries in the first matrix by the column entries in the second matrix and sum the results. By the row entries in the first matrix by the column entries in the second matrix and sum the results for each corresponding entry. Okay, so one thing that we need to say that if we have an M by N matrix, okay, and then we say we have a N by C matrix. C is not the same as M. Okay, we can multiply these together, but these N's have to match up. Okay, the dimensions have to match up so that the columns in the first the column numbers in the first matrix have to add up to the row numbers in the second matrix. These must be equal in order to multiply. Okay, so the columns in the first matrix have to add up, have to be the same as the rows in the second matrix. Okay, otherwise you cannot multiply. So we need to make sure the dimensions are correct. Okay, so let's do an example of this. So if A equals -2, 1, 3, 4, -2, 6, and B equals -4, 1, 3, -1, and -9, 2. Okay. And notice what the dimensions are on my matrices. This is a 2-row by 3-column. This is a 3-row by 2-column. And do these threes match up? Yes, they do. Okay, so I can multiply. Okay, so if A and is equal to that and B is equal to that, then find A, B. Okay, and notice that matrix multiplication is not commutative. Okay, AB is not the same. Excuse me. AB is not the same as BA. Okay, multiplying in reverse would give me a completely different matrix. Okay, AB is not the same as BA. Okay. Okay, so let's go ahead and multiply these two matrices together. -2, -1, -6 times -4, 1, 3, -1, -9, that's a 9, and 2. Okay, so I take the first row here. I'm going to highlight this. I take the first row and pair up with the first column. Okay, first row with first column. And so that will give me the first row, first column entry if I multiply the products of each of these entries. The 1, 1 entry here gets multiplied with the 1, 1 entry there. And then I keep doing that throughout the entire row and throughout the entire column. And I keep a running sum of this. Okay, so let me show you how this works. So -2 times -4 plus 1 times 3 plus 3 times -9. And that is my, and that sum will be my first row, first column entry. Okay, let's go to the second row, first column. Second row, first column. That's going to be located right down here. Second row, first column. So that's -4 times -4. Okay. And then -2 times 3. And then this is 6 and -9. Okay, and then we're going to move on to the first row, second column. Okay, so first row, second column. If I do first row, second column here, okay, then that's going to give me the first row, second column entry. And so that's going to be -2 times 1, okay, plus 1 times -1, plus 3 times 2. Okay. Now we'll go to the, hold on, and highlight this, circle that. I'll go to the last pairing, which is the last row, second column. Okay, so that becomes -4 times 1 plus -2 times -1 plus 6 times 2. Okay, so now let's just kind of clean this up. Okay, this is going to become plus 3 plus -27. This is 16 plus -6 plus -54. Okay, this is going to be -2 plus -1 plus 6. And this is -4 plus 2 plus 12. So 8 and 3 is 11. So subtract 11 from 27, that's -16. Okay, 16 and -6 is 10. Subtract put that from 54 and we get -44. Okay, this is 3 and 6, -3 and 6, which is 3. Make this closer. And then 14 minus 4 is 10. That's my resulting matrix. Notice that it's a 2 by 2 rows and 2 columns, which is not by coincidence because we start off with a 3 by 2 times a 3 by 2. Oh, sorry, but times a 2 by 3. Other way around. We start off with a 2 by 3 times a 3 by 2. Okay. 2 by 3 times 3 by 2. And the resulting matrix, these matched up, and the resulting matrix is a 2 by 2. It's just the outer, the ones on the outside. Okay. So the dimensions will tell me of the matrices. After I multiply, will tell me what the resulting matrix will look like. Okay, the dimensions of the resulting matrix. Okay. We'll formalize that into a statement. An m by n matrix and n by p matrix, m by n and m by p matrix, okay, will create an m by p matrix when multiplied. Okay, matrix multiplication, like we had said before, is not commutative. Means we can't multiply in any more order. AB is not the same as BA. If we had multiplied A times B, we would end up with a 2 by 2 matrix. But if we multiply B times A, we'd end up with a 3 by 3 matrix, and those are not the same dimensions. Okay, we say that when we multiply A times B, we are pre-multiplying B by A. Okay, we're taking B and we're pre-multiplying A. We can also state it the other way, is that if we have B times A, we are post multiplying B by A, post multiplying. Whatever your frame of reference is, okay, is our frame of reference the A, or is the frame of the reference B? Okay. The frame of reference is B. We can say that we are pre-multiplying B by A. Post multiplying B by A. Okay. And then again, we could even say that, for A, B, we could say that we are post multiplying A by B. Okay. So again, it just depends on your frame of reference. Okay. It's just some terminology. Okay, let's take some 2 by 2 matrices and multiply them together. Okay, A is equal to 3, -1, -2, 4. A is equal to that, and B is equal to -5, 2, 3, -2. -5, 2, 3, and -2. Okay. Let's multiply A times B. Okay, AB. What's AB going to be? Okay, again, that's first column, first row. Okay, and so that's going to be equal to 3 times -5 plus -1 times 3. Okay. Now we'll do first row, second column. So first row, second column, I'm going to move over. For that, that's going to be 3, 2 plus -1 and -2. Okay. Okay, now we're going to go second row, first column. That's going to become -2, -5 plus 4, 3. And then, I guess I should have said that. Second row, second column. Oops. Okay, second row, second column. And we want -2 times 2 plus 4 times -2. Okay, let's multiply that together. This becomes -15 plus -3. -15 plus -3 is -18. So that equals -18. Okay, we can go over to the next entry. 3 times 2 plus -1 times 2. Well, that's 6 plus 2, which is 8. Okay, I'm just doing some of the multiplication in my head and addition. Okay, let's go down to the second row, first column. -2, -5 is 10, plus 4 times 3 is 12, so that's 10 plus 12, which is 22. And then the next one is -4 plus -8, the last one, and so that's -12. Okay, so that's what A times B is. Okay, let's do B times A, just to show that this is not commutative. Okay, now do the dimensions work? Yeah, the dimensions work because we're just multiplying 2 by 2 matrices. So a 2 by 2 times a 2 by 2 is going to give me Okay, the middle entries are the middle dimensions match, and so the result is always going to be a 2 by 2 matrix. Okay, so the dimensions are fine. Okay, and multiplying together, we probably should have checked that at the very beginning, but it's fine. Okay, let's do it backwards now. Let's do B times A. So maybe I'll write matrices in order. Oops. Okay, so what was B? B was -5, 2, 3, -2 times A, which is 3, -1, -2, 4. Okay, and so that is going to be equal to, well, we're just going to match things up here. First row, first column is -5 times 3 plus 2 times -2. First row, second column is -5, -1 plus 2 times 4. Second row, first column is 3 times 3 plus -2 times -2. And second row, second column is 3 times -1 plus -2 times 4. Now I have to do is simplify this. This is -15 plus -4, which is -19. This is moving over 5 plus 8, which is 13. The next one is 9 plus 4, which is 13. And this is -3 plus -8, which is -11. Okay, and notice that when I multiplied A times B, I did not get the same result as B times A. Okay, so they are not commutative. It doesn't, you cannot multiply in any order and get the same result. Okay. The identity matrix I sub n is an n by n matrix okay, is an n by n matrix with ones along the diagonal and zeros everywhere else. Okay. It has the property such that A times the identity matrix is equal to A. And conversely, IA is also equal to A. So in this special case, it is commutative, and we just get out whatever we started with. Okay. We could do a small example of that. If I had 1, 2, 3, 4, and I multiply by 1, 0, 0, 1, which is I2, the identity matrix 2 by 2. I would take a 2 by 2 matrix and multiply by a 2 by 2 matrix. Okay. Okay, and let's multiply this out. This is going to become 1 times 1 plus 2 times 0, going row and column. I'm doing this right. Row and column. 1 times 1 plus 2 times 0. Notice the only thing that survives in this computation is the 1 right there. Cool. Okay. Let's go to the next column. Okay. What's the only thing that survives there is 1 times 0. One times 0 plus 2 times 1. Notice that the only thing that survives, so the 2 times 0, that goes away because it's 0. The 1 times 0 goes away because that's 0. So the only thing that survives is the 1 in the first entry and the 2 times 1, which is 2, in the second entry. So it's just creating itself again. Okay, I'm getting a carbon copy of the original. So 3 times 1 plus 4 times 0 . Okay, once again, I'm moved on to the second row. The first column, that's what this one is here. Okay, okay, and then we'll do second row, second column. And that's going to be 3 times 0 plus 4 times 1. So 3 times 0 plus 4 times 1. Okay, and the zeros go away. And so I am just left with my original 1, 2, 3, 4. Okay, so this was A times I2. Okay, where A was a square matrix. We don't have to have a square matrix as long as the columns in the second matrix match the rows in the first one, or rows in the second one. The columns in the first matrix have to match the rows in the second one. Okay, let's look at the properties of the transpose. Okay. Matrix A plus C transpose is equal to A transpose plus C transpose. Not cool. And matrix A times B transpose is equal to B transpose times A transpose. That's interesting. Okay, the product of two lower triangular matrices matrices is again a lower triangular matrix. Okay, and the same is true for upper triangular matrices or diagonal matrices. Okay, so also works for upper triangular matrices. Well, Okay, a little calculus with our matrices. Okay, calculus of matrix function. Okay, we just differentiate each entry individually. Okay, if we want to take the derivative. So say that A is my matrix, then dA dt equal to d dt of each individual aij of t. Okay, it's a function of t. Okay, for each individual matrix, then it just takes the derivative of each individual entry. Okay, so we just differentiate each entry individually. Okay, if I want to take the derivative of the product of two matrices, dt of AB, that's going to be A times dB dt plus dA dt times B. So this is kind of like the product rule. Interesting. Okay, and if we want to integrate a matrix, the integral from A to B of A of t, we just integrate each of the entries. So we're going to integrate from A to B each individual entry, A ij of t dt. Okay, so integrate each entry individually. Okay, so that is section 2.1, or sorry, 2.2. I'll see you in the next video.